Okay, so now we're going to look at situations where mass can cross the boundary. Okay, and a system where mass is crossing the boundary, oftentimes we call it, or at least the book, and I guess it's fairly commonplace for those types of systems to be called control volumes rather than open systems, which would seem like the obvious name. But um, so a control volume is a system like this where mass is crossing the boundary. There's reason for it, but don't let it confuse you. So the two types of systems we have are closed systems, which mass does not cross the boundary, and control volumes where mass does cross the boundary. All right. So from our point of view, mass is conserved. Okay. Uh, the conservation of mass is not strictly speaking a rule of nature, right? Like you violate the conservation of mass when you burn gasoline in your car engine. You violate the, nuclear reactions violate the conservation of mass. Mass, strictly speaking, is not a conserved quantity. However, unless you have chemical reactions or something like that going on, you can treat it like it's a conserved quantity. So we have a mass balance equation, which is analogous to the energy balance equation, where we have a system, present inside the system is a certain quantity of mass. Mass enters and mass leaves, and the change in the mass of the system's got to be equal to the difference between what came in and what left. And we can express that in rate form, just like we could the energy balance, where we have the rate of change of the mass in the system is equal to the rate at which it came in minus the rate at which it leaves. And this quantity m dot is known as the mass flow rate, which makes sense, and it's the amount of mass coming in or leaving. And there's another quantity called the volume flow rate, which we've introduced, and it's essentially the volume of the fluid which comes in, which enters or leaves the control volume. Now, for there's a special property of certain fluids. Certain fluids are incompressible, considered incompressible. In that case, what we're saying is that the density of the fluid, or by virtue of their relationship, the specific volume of the fluid is constant. All right. So the density is constant, or the specific volume is constant, depending on how you want to think about it. But it's basically, this is the same statement. These two statements are in fact the same statement. Okay. Now we have a special property that is going to apply to pretty much all of the systems that we are going to be analyzing, all the control volumes that we're going to be analyzing, and that's the steady, if it's a steady system. All right. So you could think of these properties versus time. Okay, this could be any analogous property. When you first start up a device, say you first start up a pump, maybe it takes a short time for the pressure to build, and then maybe it overshoots and comes down, and then but eventually these oscillations settle out, and at some point that value becomes constant. Okay, and likewise, so this could be, like, say this could be the pressure. Maybe you have the temperature. Maybe the temperature is a little bit um, less, it doesn't oscillate or whatever at the beginning, but it still has the same property that at some point after a certain amount of time, this could be this temperature. So like you turn on the pump, it starts to warm up, right? And as it warms up, it starts to give off heat, and at some point everything balances out and it smooths out and everything becomes constant. All right, so we are only going to be interested in the point. So this is where things become steady, and this is like, these are called transients. So we're going to be interested in situations where these properties become steady. All right, and so specifically, the rate of change of the mass within the system is going to be zero. So if I plotted the mass, maybe the mass would actually maybe shoot up very quickly and then level off or something like that. You get the point. At some point, at some time scale, things kind of settle out, and we're going to be operating in the steady regime for the most part. All right. So that's the idea. And so, if a flow is steady and incompressible, then if it's steady, uh, dm dt uh, equals 0. So therefore, m dot in equals m dot out. This is actually true up here as well, right? So for a steady process, this is true. For an incompressible process, uh, the volume flow rates can be equated. This isn't going to be terribly useful for you for this class, but it's something important because sometimes the quantity of a fluid is given to you in volume flow rate, and you have to understand. I'm not going to do that to you probably, but you might see the air entering a duct as given in terms of cubic feet per minute, and you have to understand that if the temperature is changing, um, say, then the density is going to be changing, and the volume entering and leaving may differ, even though the mass is staying the same. So this is true for steady and incompressible. This is true for steady. This is true for steady, and for this to be true, it has to be steady and incompressible. Well, actually, that has to be steady and incompressible. No. Yeah, actually both. So, okay. Now, I guess we can rehash some of, before I go into the examples, we rehash one important quantity. The total rate, so the rate of specific energy transport via mass. Okay, so recall the uh, and this is just to rehash this, but I mean, I've already spoken about this. So this is given by the quantity theta, and if you remember, that's equal to the internal energy of the fluid as it enters, plus this quantity, this special quantity for flowing fluids called the flow work, plus the kinetic energy per unit mass, plus the potential energy per unit mass. All right, and then we can combine these two to that new property we called enthalpy, and so theta is just the enthalpy and then the rate of energy transport into the system via mass. So I guess I'll call it E dot mass is just the mass flow rate times theta. One more thing. There's a keyword that we're going to be using um, that I should define before we get started, and that's adiabatic. That really just means uh, it's well insulated, meaning that the heat transfer through the boundary can be considered to be zero. That's what adiabatic means. Okay.